Hello. Many people have asked me about the relationship between the E field strength, the potential strength, and distance. And there is actually a simple relationship between them. I'll try to explain that and give you some intuition for it here in this video. So let's get started. So let's imagine a situation like this where we have two plates. One's at minus 10 volts and another one's at positive 10 volts. This one has plus Q charge on it. This one has negative Q charge, exactly the same amount but different sign. Now we know something about the electric field. This is a formula but for two parallel plates. The E field equals the charge on one of these plates divided by the area of the plate times epsilon naught. And what that means is that the field between these two plates is not dependent on distance. There's no R in this formula at all, as you'll notice. So the field is indeed just a bunch of constant lines going from one plate to the other, like that. Now the question is, what is the potential? Is the potential also constant, or should we imagine the potential to be somewhat different? Well, think about it. The potential here is plus 10 volts. The potential here is minus 10 volts. So that alone should tell you that the potential is not going to be constant between the two plates. So let's take a look at it. So now we're going to plot it. So here's potential on the y-axis like that, and here's distance between the plates on the x-axis. What does it look like? So it looks like this. So we start out at minus 10, we go all the way up to positive 10, and this has to be a straight line right between the 2 points. And that tells us that the potential somewhere around in here is going to be near 0, and then somewhere around here it's probably going to be, 5 or something like that. We can represent that by this, well, let me just draw the diagram here. Here's the diagram. So it means that the potential starts at minus 10 volts if you're going from left to right, climbs to minus 5, goes to 0, climbs to plus 5, and then goes to 10, positive 10. So it changes by a constant amount with distance. So one way to describe that is to imagine I told you I wanted to know the potential of this point right here that is 0.75 meters from the left-hand plate when the distance between the two plates is 1 meter. How would you do that? You'd say, well, the potential at point A is the potential of the negative plate, if we're going from the left, plus the distance that you've traveled from the left-hand plate times the difference between the positive plate and the negative plate. So the voltage at point A is minus 10 volts because you start out at minus 10 volts here. And then it's 0.75 meters. You've traveled 0.75 meters from left to right of that total difference. What's the total difference? It's from 10 volts to minus 10 volts. So it's a 20 volt difference when you go from the minus 10 plate all the way up to the 10 volt plate. So I'm taking this distance and multiplying it by the total difference in voltage. That's what we're getting here. And we're starting out with whatever point we're at when we start out on the negative plate. So this is the equation that gives us the voltage or the potential at any distance between these two plates, if we know what their potentials are at the ends. And we know the difference between them, the distance between them. And so the potential at point A is just starting out at minus 10 volts, but then you climb 15 volts, so the total is 5 volts. So that's a specific concrete example. And you can also probably tell just by intuition, as we showed earlier, that if this plate is at minus 10 and this one's at positive 10, then it's got to be basically equal intervals of 5 volts as you go across certain fractions of the distance. So that's what it would look like. Now, I want to get at a slightly deeper and more useful concept here, is that you can use this equation here. In general, the electric field equals the potential divided by the distance. So more specifically, it's the difference in the potential divided by the distance. So if we wanted to know what the E field strength is here between these two capacitor plates, we'll take the difference in potential between one plate and the other, if we're going from left to right. And what we can do is we can say, okay, it's going to be 10 volts minus 10 volts, and that's a total difference of 20 volts in 1 meter. So that is a way of describing the electric field strength in volts per meter. Now, that also leads to this idea of what happens if these lines of different voltages are closer or further apart from each other. Well, you should be able to imagine what's going to happen there because of this equation here, how it depends on distance, right? So let's take a look at something like this to illustrate. So imagine we have a 1 coulomb charge, a point charge like that, and the formula for the point charge potential is this, kq over r. So this does depend on distance. The further away you go from the point charge, the smaller the potential is going to be. And you've seen this sketch before. It looks roughly like this. So here's going off in the positive r direction, here's in the negative r direction, and we'll call this the origin. So as we go away, then it falls as 1 over r. It falls off like that. Okay, so it looks like that. Now, I can draw potential lines, isopotential lines, that match this graph. So imagine I had sort of a three-dimensional construct of this, and I built some sort of funnel, and I painted little circles around it at different levels, at different voltages or different heights. Okay, so the idea is that the distance between these two circles is meant to be the same in all these drawings. Okay, now what would that look like? Well, here it's going to be very steep. So even though the height between these two guys is the same, the distance between this one and this one, at least in terms of lateral distance, isn't that much. So that means you have a large change in potential for a relatively short distance traveling sideways. And that just means that this part of the mountain is very steep. Whereas if you go down further out in this 1 over r potential, then what you get is something that's very shallow. Now, this idea of a steep change in height, you change a lot in potential over a very short distance versus you change a little bit in potential over a longer distance, that should capture the intuition behind what the E field strength is. So for a point charge, you have a lot of change close to this charge, and then as you go further out, it's not as much change. So if we apply our formula, the electric field is given by the change in voltage divided by some distance, then here that means we're going to have a very large electric field as we get closer and closer to the point charge. If we're further away from it, we have a small, shallow slope, and so we're going to have a weaker electric field like that. That's the idea. One of the things you did in lab, I know, is you looked at some sort of topographic map. So for example, imagine a mountain. And let's say this mountain, everything on this curve right here is roughly 100 meters above sea level. Everything in this curve is 200 meters above sea level, 300, 400, and 500, and so on. And if you're planning a hike to get to the top of the mountain, you can immediately see that there are two choices. You could go this route, this sort of red line like this, as you go up this way. And that's sort of a gentle, shallow path. It takes a longer distance to go from 100 meters to 500 meters. Or if you're really into tough challenges, you could basically do this steep path right here. And that is not very long, but you go from 100 meters to 500 meters. So you have a difference of 400 meters in a relatively short distance. And so you would know that this is very steep. That would correspond to a very strong electric field, and this would correspond to a weaker electric field. And again, the equation is basically E equals the change in V divided by the distance. So the more rapidly the potential changes for a given distance, the stronger the E field is that you have. That's it. Hopefully this was helpful.